why don't I write, or why do I not write those together, but write them separately? I mean, this is just the square of a plus b squared, which normally is a squared plus 2 times ab plus b squared. But I didn't write that. I wrote it actually explicitly out. Well, that has very much to do that this is the gradient operator. And that gradient operator takes the derivative of everything which is standing behind. Now this is part of the Hamiltonian, so eventually the whole thing is acting on a wave function. So if I look at this term, let's take this one out. Pi dot A of R at the position Ri. Then I should think of that I have a wave function behind that. Yes?
I'm a little confused about your 1 over 2 ME. I'm assuming that everything to the right of your sum is part of the sum because you have Pi multiple places. So how are you getting, in principle, 1?
Oh yeah, sorry, I missed the sum. Thanks.
Okay.
Yes. Sorry. Thanks a lot. Good. So this is minus IH bar times the gradient operator, that P. So that's a derivative, and here I have a product. So this is the same as minus IH bar, and then I take the derivative of the first term in the product. So that's, and in order to make sure or distinguish that this is now only the derivative of the vector potential, I better put a parenthesis around it. Times psi plus, and now I take the derivative of the second part. So I get A, and now the P acting on A of Ri, the P acting directly on the wave function. This is a product, so I have to use the product rule. So I get 2 terms. Where here this is the gradient of the vector potential alone, and the result then acting on psi, whereas here I have first the momentum operator, the gradient operator, acting on the wave function and afterwards. And this one, that's the same as this one up there. So I could write that this thing is, I mean the whole parenthesis I could write it as twice this one, and then this. Now, those vector potentials, they are defined implicitly. You can see, I mean, this is sort of this is the definition of the vector potential, but that's a definition where the vector potential is sort of standing on the right-hand side. It's not an expression A is equal to something. It is an expression that you get something else if you do something to A. And that's the one we start from. So it's indirectly defined. And this has severe consequences. I mean, the same up here. Let's think about that first. I mean, this is the gradient, so that's the derivative with respect to the position. So it looks at the change of the vector potential with respect to the coordinates. How does that scalar potential change in space? But if I add some constant to that scalar potential, that constant disappears when I take the derivative. The same also happens here. which I can add something to both potentials, something which corresponds to a constant, and it will not change the fields. So there's some freedom in the definition of those potentials. To a scalar potential, I can always add a constant and it will not change the electric field. And similarly, I can do things with a vector potential. And the different choices of how one defines the vector potential, they are called gauges. And it all leads to the gauge problem of magnetic properties. And one of the possibilities one has, and I'm just show you that, but I mention it, but I don't derive it. One of the possibilities is that I can set this actually to 0. I can choose or define my vector potential in the way that that's called the divergence. If you add some electromagnetism, this up there, the cross product is the curl. The scalar product of the gradient operator and the vector potential is called the divergence. I can set it to have 0 divergence. This has no influence on that up there. Even if I choose my vector potential to be like this, I still get the same magnetic field out of it. So I did not change the physics. I just changed the mathematical representation of that field. Because those potentials are in a way a mathematical way of representing the fields. And I didn't change the physics, I changed the mathematics, yes. And this particular choice is called Coulomb. And then gauge, that's the word. With that Coulomb gauge then, I can write the whole thing here as 1 over, I don't want to write it there, I'll sort of put a parenthesis around here and write it down there. Then I get 1 over 2 me sum over all electrons, canonical momentum squared, so that's just the normal kinetic energy term. And now I get, because now I have this twice, which goes out with the 2 here, so I get E over me sum over all electrons, and then I get the vector potential at the position of the electron, scalar product with the canonical momentum, and I get this extra term E squared divided by 2 me, just the square of the vector potential, like this.